Good afternoon, everyone, and welcome to the 6th Women for Space conference organized by Women in Aerospace Europe, Barcelona. I am Judith Hernandez, a board member of WIA, and now I am going to introduce you who we are and why are we organizing this event, and later present to you our today's speaker, Mercedes Herreras. Welcome and thank you for joining us, Mercedes. Women in Aerospace Europe, Barcelona is born encouraged by professionals and enthusiasts of the space sector with the aim of expanding women's opportunities for leadership and professional development while increasing their visibility, as well as motivate girls to get interested in science and, last but not least, communicate the key role that space plays in our daily lives. Today, our host speaker in this Women for Space Talk Cycle conference is Mercedes. She holds a master's degree in aerospace engineering, and today she's going to talk about NASA's VIPER mission and her tasks on it as a risk manager in NASA's Ames Research Center located in California, Silicon Valley. If you have any questions, you can write them in the chat during the presentation, and we will manage them after Mercedes' speech. Thank you and enjoy this talk. Mercedes, the floor is yours.
Thank you. Thanks so much for inviting me to chat with your great initiative. So let's see. So a little bit about me. Let's see. Can you guys see the change of slide? There you go. So I studied aeronautical engineering in Barcelona at the UPC, as Judith is doing right now. And then right after I finished my degree in aeronautical engineering, I moved to the US, specifically to Phoenix in Arizona. And I did my master's in aerospace engineering in the University of Arizona State University. And then during my master's, I was working in a space lab where we would work in different CubeSat missions, especially the conceptual phase and also the pre-design phase of these missions. And then I got my first internship at NASA JPL in LA, which is the center that does all the Mars rovers. As you might have seen lately, they just landed one on Mars. And then right after that summer internship, then I graduated, and then I got another long internship at NASA JPL working in a small CubeSat hybrid propulsion. So hybrid is solid fuel and then gaseous or fluid oxidizer. And I also work as a systems engineer for Europa Clipper, which is another one of the big probes that they are going to send near Jupiter to explore one of the moons. Europa is it's an icy moon. And so I did work for that mission as well, doing a lot of thermal engineering, mechanical engineering, materials engineering. And right after that, I got two offers, one from NASA JPL and another one from NASA Ames Research Center, which is is not South California or kind of central South California like LA, Los Angeles. It's north of California. And so I accepted the offer at NASA Ames Research Center, and I am currently working as a risk manager and also the technical interchange lead for the mission. So let's see, next slide. All right. So this is a chart from NASA that shows some of the previous missions to the moon, such as the Lunar Reconnaissance Orbiter. You can see it right on the top left, which was kind of like the granddad of lunar science. And of course, Artemis missions, which are maybe you're familiar, they are like the new Apollo missions, which are targeting to bring humans and the first woman back on the moon. And they will include building the lunar gateway and do scientific experiments on the lunar surface and so on. So I encourage you to go and look up more what the Artemis program is. It's really, really, really cool. There's also the CLIPS, so the Commercial Lunar Payload Services, which is like bottom left, which I will explain later, but they are enabling our lunar delivery to the moon. So as I will emphasize later, VIPER is a pathfinder in relying as well on the commercial sector to deliver the rover, our rover on the moon. So in many ways, VIPER is a pathfinder, which is good and bad. But today I'll focus, of course, on VIPER, which is the yellow circled mission right in there. Let's see, next slide. All right, so let's go into the lunar resources topic. I'm not an expert on this, but I know the basics or fundamentals. So this slide shows the natural progression of the resource hunt turning into a resource that is going to be utilized, which is pretty similar to the approach that we use on Earth. In the case of the moon and lunar resources, you start with orbital observations and the whole idea that there could be water ice. So some orbital observation missions led to think exactly that, which was strange because of the, I don't know if you guys have heard of the Apollo missions. They just thought it was a very sterile environment. So then you continue with observations, with more directly prospecting. And when you're prospecting for a particular resource of interest, it's really, that's what's really prospecting. It's you look for a particular resource of interest, not just looking in general. Then you create some maps, but then you need some kind of ground truth. So you need to convince yourselves that what you think you know, you now understand, it's the case, and then you need to calibrate, and that's probably like you need to check that what you saw, it's actually the compound that you saw, what's the concentration. So that truth of the, you know, that what you think you know from the orbital measurements is actually correct. And so when you've done the ground truth, then you want to do actual prospecting. And that could be done with humans, or it could be robotics, or a combination of the two. And so you need to go find the stuff of interest, and then you specifically map out those resources of interest. And that rolls into in situ resource utilization, meaning you need to demonstrate ways in which you might harvest or utilize what you map. And then the final stage is probably like some bulk production, and you're making some kind of wholesale utilization of what you found. So there's a series of missions here that you can see on the bottom of the slide, where you can see the different steps of this process, how it maps to the different missions. So there's a Clementine mission, which I think it was a DoD mission, that's why it's in black. And then there's L-Cross, which is a really, really fun mission in the late 2000s. It was the iconic lunar orbital measurement and mapping mission of all times, to date, at least. So it did amazing observations and prospecting. So they sent it an impactor into a chosen permanently shaded regions. You will hear me using that term a lot. We call them PSRs, permanently shaded regions. So these regions are regions on the moon that have never seen the light of sun in millions of years. So they chose one of these PSRs in the south pole of the moon, and then they impacted with an impactor. They impacted that area, and then they watched what got kicked up of the impact, and they measured it. And that was the first ground truthing of water as crystal water, and also as the vapor that sublimated once it came out, since there's no liquid phase in vacuum at these temperatures. So VIPER is going to be doing some ground truthing as well, prospecting and resource mapping, which then can be followed by future missions or industry. And then this data, basically these industries will need VIPER data to determine if the mechanisms that they are coming up for extraction or harvesting this water are relevant or not. So, I mean, you can imagine harvesting water that is more superficial might be very different than water ice that is like 1 meter down in a very, very dark and cold environment. So, let's see. All right. So why VIPER? So it wasn't clear once the L-cross, the mission I was talking about, impacted on the moon, whether the hydrogen was just element hydrogen entrained in the soil, or it was bound, or actually water, water ice as H2O. So VIPER is exactly doing that, going there and actually checking what it is. And VIPER will also be revealing the ore grade availability of lunar volatiles. So that's a term that our project scientist uses. So ore grade is in effect a threshold concentration and availability that makes the resource useful, right? That makes that thing a resource, actually. So Sophia, which is the flying telescope, the one that is mounted on a huge plane, has found water in other sunnier areas on the moon, but that doesn't make it usable. So VIPER is trying to answer that question as well. Like, sure, there is water, but if it's too difficult to get, is it really a resource? So let's see, next slide. All right. So VIPER then is trying to answer key questions for both science and exploration. So for science, it's trying to understand the moon water, which will help us understanding other airless bodies where water is also observed. And it will broaden our understanding of maybe history and the role of water in the inner solar system. And then there's also helping exploration in helping understanding the resource potential and addressing the key theories about water emplacement and retention. So what VIPER will do is to, these are a little bit like the science goals that we have. So it will evaluate the distribution, so vertically and laterally. Vertically because we have a drill, as I will explain later. So we'll take like bites or samples at different depths, so we can understand how the water concentration or distribution varies as we go deeper, and laterally because we're roving around and understanding how it varies from drier regions to maybe more wet regions. So we will also be characterizing these volatiles, including the distribution and the form in 3 different regions and in a dry regions. I'll describe the different regions that we have. And then it will correlate the type of these regions with the total water ice availability. So we'll try to understand, oh, so it looks like this type of region has this amount of water. And it looks like this other type of region has maybe more water. So we'll try to do some kind of like hydric or hydrologic mapping of the moon in some way. Let's see. All right, so yeah, as I was mentioning, we have classified the different regions that we're exploring. We call them ice stability regions into 4 different types. So there's what we call surface or superficial, which is regions where we expect ice to be at the very surface. And that we believe might only happen in these PSRs, permanently shaded regions. And we might be wrong, but that's what we think when going into it. And even if we're wrong, we will have the data to correct our assumptions and adjust the definitions accordingly. So then we have the shallow regions, which ice would be expected to be stable between 0 and 50 centimeters depth of the surface. Then deep, which is between 50 and 100 centimeters of the surface. And then dry, where we wouldn't expect any ice to be stable in that 0 to 100 centimeter range. So this is another cool picture about how these PSRs, most of the time these PSRs are in craters. Those craters, because of the very low angle at which the sun incites the surface of the South Pole, they never get illuminated because of the orbital dynamics of it. And then let me just jump into the thermal environment. Okay, so another, I'll talk deeply, not deeply, but I'll cover the challenges that the mission has. But some of the challenges associated with the mission in the polar lunar is really the polar lunar temperature in space, and is a really, really tough problem. So the Apollo missions and many of the missions to date, they really focus in mid-latitude, not necessarily equatorial regions, but not far off of equatorial regions of the moon. And so what that means from in terms of lighting conditions is that roughly you have 14 days of sun and 14 days of night. As you remember, like the moon takes about 28 days to go around the Earth. So basically that's a lunar day is 28 days to 28 Earth days is a lunar day. 14 days are of sun and 14 days are of night. But when you get to the poles, it's something similar to what happens on the Earth poles happens there on the moon as well. So you get very long days and short nights during the summers of the moon as well. But it's a bit different. It's more extreme. Lighting in the moon is actually very different because there's no atmosphere. So there is no scattering of the light. So you go from light to darkness very quickly. And it's very like there's a high contrast. If you've ever seen some of the Apollo pictures from the astronauts, you'll see that the shades are very, very dark and the bright part, the sunny part is very bright. And so you also go from very warm to very cold very quickly. And as you can see in the graph, in some of the places we're exploring that, for example, have PSRs, we get to temperatures that can be around 30 Kelvin, which is really cold in PSRs, but then temperatures that are 10 times higher in sunlight regions. So this might give you an idea of how hard it is to design a rover to withstand those ranges of temperatures. The Mars rovers don't have to deal with this. They have cold temperatures and warm temperatures, but not nearly as bad. So especially the cold ones, we need to be able to store enough energy on our batteries via solar power generation because we don't have radioisotope generators, the RTGs that the Mars rovers carry. They're basically powered by nuclear radioisotopes. We cannot do that because we were declared to be a fast space mission, and in order to carry like RTGs, you have to be a higher class mission. There has to be a lot of safety and a lot of like procedures to handle these things. So the mission would not be able to be fast paced. It would be a much longer mission. Like the Mars rover missions, I think, are about 10 years, if I'm not wrong. Ours is a mission that is happening in about 3 years. It's fast paced, but it still has to be successful. So where was I? So yeah, during these short nights, we will have to do something with the rover, right? It's going to be a very cold environment. So what we'll do is we will hibernate our rover, keep mostly everything shut down, and just use all the energy that we were able to gather, which basically will be full charge of our batteries, to keep everything alive with our thermal system, with our heaters, to try to keep everything within the operational temperatures that hardware was designed to survive, which they are not nearly close to 30 Kelvin. So we need to keep everything for like, I don't know, ranges of maybe minus 40 to plus 60 degrees Celsius. So it's still a lot of energy to keep everything in those ranges. So even if this looks, complicated, summers on the moon are partially what makes our mission work. Because imagine if we would have to survive 14-day nights. We don't have enough energy. We don't carry enough batteries. It would have to be very bulky rover to carry enough batteries to survive so long. So these short nights are a good thing because then we can survive the night instead of having a mission that only happens during the lunar day. So let's see. Okay. So this is a little bit our VIPER timeline. So we started with the formulation through the requirements lockdown in 2019. We had our preliminary design review last year in August. Now we're heading into our critical design review, in which the design of the rover is mostly detailed, and you're supposed to start fabricating right after. So we're having in October our critical design review. Then we have system integration and test, where we put everything together and we test it in 2022. And then we're targeting launching in November 2023. And our mission will conclude about March 2024. Let's see. So now a little bit on the VIPER science specs. So our mission duration is about 100 Earth days. Let me just put the screen in front of me. So our mission duration is about 100 Earth days. We carry 4 instruments. So one is a neutron spectrometer, the other one is a near infrared spectrometer, and a mass spectrometer. And we also carry a drill that is able to drill all the way down to 1 meter. We also can detect concentrations of water of 0.5% per weight. And also, I think I already mentioned the drill depth. We will also do about 30 to 40 drilling activities throughout our mission. As I mentioned, in these hibernation periods, when the night comes, we have a survivability of about 70 hours. So we need to find traverses, as we call them, like little, paths for a rover to do. We need to find traverses that will, when the night comes, we can stay at a spot where the night duration or the darkness duration won't be longer than 70 hours, because that's our maximum survivability. And then we also can survive about 8 hours with our rover working inside one of these PSRs. So there's darkness, but we're working, we're drilling, we're prospecting. And then average, we plan to travel about 20 kilometers throughout the mission. And as I mentioned, the critical design review is right now is in the 3rd quarter, I think, of year 2021. Then some performance specs. This is all they allow me to give. About the rover. So it's about 430 kilograms mass. So just imagine it's about the size of a golf cart. You know, these golf carts that when you go play golf. I don't play golf, but people do. So it's about that size. Then our solar panels are able to generate about 320 watts per array. But if you put the corner facing the sun, then you can get the square root of 2. And it's about 450 watts. Then we have a high-gain antenna and an omni antenna. There you can see the data rates that we can get for both. We have about 6 to 15 seconds round-trip latency. So that's how long the signal or our commands take to go there, and then to go from Earth to the rover, and then the rover to send some kind of like, hey, I got your command, I'm executing it, and go back. So it's about 6 to 15 seconds of latency. And we're also using the Deep Space Network, the DSN, which are the biggest dishes that we have on Earth for deep space communications. Then dimensions, as I mentioned, is like 1.7 by 1.7 meters, and then 2.5 meter tall. Our wheels are about 0.5 meters of diameter. We do explicit steering, which is we can steer each wheel independently, which is one of the things that we're pathfinding as well, I think, because the Mars rovers don't do that. We have active suspension, so we can change the height of our suspension, make our rover taller or shorter for climbing obstacles to make it more stable. Our top speed is not crazy. It's 20 centimeters per second, so it's pretty slow. And that's our fastest way of driving, which is rails driving. I'll explain later what it is. And then our prospecting speed, which is when we're actually taking measurements, is about half of it. We do waypoint driving. So waypoint driving is, we have an interface on the ground where you can place a little dot on a map, and then you send the command, and then the rover will move to that little dot. So all these little dots are called waypoints. and every step that the rover will take to go from one dot to the other one is about 4.5 meters apart. Fault response, well, we have fault responses. I think someone wanted to mention here that if we lose signal, we could try to auto reverse to the last point where we had communications. Lose signal, I mean, right, we lost comm with Earth for some reason. The camera look ahead is about 8 meters. We climb rocks of about 20 centimeters, not more than that, and we go over slopes of about 15 degrees. And as I mentioned before, expected cold environments are even like 40 Kelvin. Let's see. So now I'm going to go a bit into the operational plan of VIPER. See if I can find here. Okay, so another interesting thing about this mission is another pathfinding topic. Is going to be the first mission of its size by a lot to be delivered by the commercial lunar payload services. So what is this? So at some point, the evolving commercial industry was expressing interest of being able to explore the moon and provide lunar delivery services. So you're probably familiar with the big names like Blue Origin. They came up with the Blue Moon concept just to be able to land things on the moon. SpaceX, SpaceX is always after everything. But there's also small players too in the game. So a competition was held to deliver VIPER to the south pole of the moon on a specific date, timeline, and certain performance specs and mass that we put on a contract, basically. And then through the competitive process that we did, which we actually do not run, CLIPS is its own office. So we participated on the selection process, but we don't run this competition. Astrobotic from Pittsburgh was selected. So that lander that you see in there, which is the Griffin lander, they designed it, it's their deal, and they also picked the launch vehicle and picked the launch date. Although we picked the date that we want to arrive, and we also picked the X and Y coordinates, right? The location where we want to be placed on the moon. So basically, using a bit of a metaphor, we don't get into how you maintain your car, what the history of your car is, although I hope it's okay. It's not my business. You gotta get me there. It has to be a certain environment along the way, and I don't want a nasty car because I have instruments that are sensitive to contaminants. So I might need to do some calibrations of my instruments while cruising. I might need a certain power during the cruise through some kind of umbilical cord. So it's a whole different model. Like, we really don't tell them how to design their stuff, but they have to meet some requirements. They have to land us safely, not contaminated. So yeah, it's another pathfinding idea, and it has its pros and its cons. There's a lot of, when we interface with each other, we have constraints in what things we can ask to each other. So it gets tricky. So let's see. So these are surface ops, I guess. So surface ops, which is what we do on the surface of the moon, they are led out of Ames. So we have a mission ops center, a science ops center. We also do other things like project management, systems engineering, rover flight software, I think. We also do some mobility testing of the rover. We have 2 of the 4 instruments are developed at Ames. Johnson Space Center, which is in Houston, Texas, is building and designing. We are also designing the rover with them from Ames, but they are mostly building and designing the rover. Then flight software is coming out of Ames. Johnson is also doing the systems and integration of the rover, and also the readiness with Astrobotic, with the lander. So all the testing that needs to be done to integrate with the lander. And then Kennedy Space Center in Florida has an instrument as well, and they have their own ops for the instrument. And then we have another commercial partnership with Honeybee Robotics in Los Angeles for Trident, which is the drill. They call it Trident. It's pretty funny. So this is actually the map of like kind of what I was talking about. And let me now jump into a little bit of the science. So let's talk about prospecting and how it works. So this is a busy diagram, but when you get into it, you realize it's actually pretty cool. There is a cross-section of the lunar soil. So you can see the regolith, the soil in there. So that soil is being heat all the time by solar energy and solar radiation, and also galactic cosmic rays. And probably in the areas that are in the shadow, then you remove the solar radiation part, kind of. So they are mostly hit by galactic cosmic rays. So when those hit, those energies are absorbed into the soil, and they crack different molecules, and they disturb things, and so forth. And then neutrons get released. So there's a flux of neutrons emanating from the surface all the time. So it turns out that water tamps down the neutron flow from that flux. So the neutron count becomes a mean to guess where water is, even if it's under or in the soil. So the graphs on that kind of wall, they're trying to represent as we're moving with the rover, with our neutron spectrometer, we're going to see the neutron count plummet because the neutrons are being absorbed by the water when we are in an area where there might be more water. So we use our neutron spectrometer to be somehow the sniffer, and then the near infrared spectrometer and the mass spectrometer, M-SOLO. These systems are complementarily studying the products that are on the surface, and more importantly, what's being brought by the drill, the little samples or bytes that the drill is capturing, doing that vertical distribution that I talked about. So that will let us understand the water ice and some of the characteristics of whatever materials the drill is coming. So the drill will leave a pile, and then the fields of view of the instruments will be looking at the pile every time there's a new sample being gathered. This is a very powerful map that we should theoretically be able to produce after doing the mission. Okay, let's jump into the mission phases. So talking about phases, this is the astrobotic own space, like all the way to the left. So we don't control any of this stuff. We don't control whether they want to take 5 or 10 days to get to the moon. We control the date and location where they land us. And then once we get wheels on the ground, then that's our mission. We have our surface stops that last about 100-ish days, and they are broken up in traverse legs and safe havens. So for this, actually, let me jump into how the sun and the darkness periods work on the moon. Let me see if I can find the slide. I think I have a slide for that. Yeah, so this slide should probably help a little better. So as I mentioned, at lunar polar sites, we have a very, I think there's a better, okay. So if you see on the top right of this slide, you see that the clearance from the horizon on the moon with the sun is normally about, it's really, really small. I can see it here on the bottom right. So it's about like 2 degrees. You would see the sun 2 degrees elevation on the horizon. So the sun comes at a very, very sharp angle. That makes the shadows to be very long. It's crazy. You should check the pictures. And then there's a similar thing with the Earth. The Earth is also very, very low on the horizon. It's about, I think, maximum 10 degrees above the horizon. And so if you would be an astronaut was there, you would see the Earth going up to 10 degrees and down, and then up and down, and it just stays static. And so another thing I wanted to show is how our mission has to escape from the shadows as we traverse. And the shadows move at about the same speed as our rover moves. So both sun shadows and also communication shadows. So communication shadows, because we have antennas and we do direct communication to Earth, we always have to see the Earth on the sky if we want to communicate. And we are basically driving a rover from ground. So we need to have communication in order to drive the rover. So hopefully this video plays. It's pretty cool to see how the white stuff is sunlight, the dark stuff is the shade, the shadows are going after us. And so I'll play it again. The rover is the red dot, and it's just trying to escape from the shadow, but they move about the same speed. So, okay. So basically, how Earth looks relative to the moon is not so intuitive, as I mentioned. So I mentioned that we need basically we need to see the Earth to be able to drive the rover, and we also need sun for power to drive the rover. So we're not using the as I mentioned. Some people ask, why don't you use the lander as a comm relay with the Earth? And the reason is because we wouldn't be able to see the lander from many of the places that we're going. So what else I can say about this slide? So these traverse legs, this is probably better to show the next slide. We have traverse legs, and then we have safe havens. So a traverse leg, you can see. I'll introduce first what the safe haven concept is. So safe havens are basically, if you remember when I was talking about, we have a period of light and then we have a period of darkness. That because it's summer on the moon, then the period of darkness will be shorter than the 14 days. If we're trying to look for periods that are about 6 days. And then if we place ourselves in a little high hill, then we can even make it shorter. So those little places that are a bit high hill is what we call safe havens. So we need to be able to get to the places where we want to do science, because they are of scientific interest, because we think there might be resources there, which are called science stations. And rails is what we call just, we don't stop for science. We just go as fast as we can from A to B. And then the safe havens are these places where we can minimize the darkness periods and we hibernate a rover. So those are the safe havens. And we need to make it on time before the darkness comes, because if we get caught somewhere else, we cannot guarantee that the duration of the darkness is going to be that short. It might be longer. And as you know, we have a 70-hour hibernation duration. Let's see. I'm going to try to skip to some interesting things since we have about 15 minutes left. Okay, VIPER surface segment. So these are rover. As you can see, we have NSS with the neutron spectrometer right in front, is that yellow or gold thing. We have the drill. We have a star tracker for localizing ourselves. We have 4 HAZ cams, so they look at the wheels to check for like hazards right in front of the wheels. We have 2 cameras on the top on a mast, and that's for situational awareness. So we can do stereoscopic vision with that. We can also like build 3D mapping of the terrain as well. We also have a pair of cameras on the back in the case that we will need to backtrack. We have a radiator. We have, of course, a computer, and then we have the other 2 instruments, the near infrared and the mass spectrometer on the belly of the rover. You cannot see them, but they would like basically beam like view the pile of dirt that the trident drill is getting out of the ground. Let's see. I think I already talked a little bit about this. This is mostly what the instruments do. This is VIPER compared to other rovers. So you can see the first rovers from Mars, the Sojourner. Then we have the Mars Exploration Rover. That one I think is about the same size. But if you see the newest Mars rovers are bigger, like the MSL, Mars Science Lab. They're a bit bigger. And then we also have the lunar roving vehicles, which they used to be used by astronauts, by Apollo astronauts. They're decently, they're big, they're light, but they're made for a human, of course. And then let's see what else I can show. So I think this is a pretty interesting chart. So these are some of the challenges that we face on the mission. So the first thing, and I think I mentioned this already, is it's demanding for our imaging system how long the shadows are and how big of the contrast it is between the very bright sunlit area and the very dark shadows. There's also uncertainty on the number of rocks and craters that there will be in this area. We have all the data we have is actually data from imagers, so from satellites that at some point did some kind of mission, but those pictures are about 20 meters per pixel, so not great. You cannot really see certain sizes of rocks or craters. And then we also have pictures from the Apollo missions that the astronauts took. So we have people actually counting rocks and craters in pictures, trying to understand how many rocks per surface area there is. And we're just extrapolating this data. This is not great. Also, we have, as I mentioned, the uncertainty on the trafficability because we have the 20 meter per pixel images. We're trying to get these images better by doing something that they call shape from shading. So by looking at the shapes and the shades of the images that we have, they can try to extract like a better resolution of these maps, and they are really actually trying to push it down to a 1 meter per pixel. So I have no idea how they get this so well. Let's see. So we also have, as I mentioned, the elevation of the Earth on the horizon is very low. So when the Earth is so close to the horizon, that might create some kind of interference that they call it multipath interference of our RF link. So that is another thing that there's a lot of research now being put agency-wide. NASA is investigating a lot on how to overcome multipath interference because the regolith reflects weirdly the RF electromagnetic basically signals, and so as you move, your signal strength might change because of that interference. Let's see, we have very variable temperatures. We have the sun and the calm shadows moving as fast as the rover. Another thing that is tricky is that it's very hard to find analog environments on Earth to the moon. Like it's really tricky to generate a 1/6 gravity regolith environment. It's also like the way the grains of the regolith would interact with your wheel is different with a 1G, it's like gravity on Earth, than if it's like 1/6 gravity. So things like traction of your wheels with the regolith is hard to estimate if you are in a 1G environment versus a 1/6 environment. So traction is another thing. Like, I guess we will have good traction. And then another challenge, as I mentioned, is interfacing with our CLIPS partner because the fixed price contract nature that I described. And also that we're Class D mission. So Class classes of missions in NASA are, to say quickly, Class A is the typical mission where you don't tolerate risk at all, because, for example, you're carrying astronauts, so you don't want your astronauts to die. Class B are normally like very, very expensive missions, such as, I think the Mars rovers are probably Class B, as in Bravo. Also very expensive probes that go to like Jupiter, Saturn. So then there's Class C and then there's Class D. So Class D, they're really highly tolerant, like failure is okay. And so there's also less budget. So we're a fast-paced mission with not so much budget, and we tolerate risk pretty highly. So you have to be pretty smart on how you pick your battles, basically. And I think these have been commented more or less throughout the chat. These are shown. These are shown. This is basically in the local summer, as I mentioned on the text on the central left. We have nights of 7 to 10 Earth days a month. But if you pick and choose those little hills that we call safe havens, you might be able to reduce this to like 0 to 4 days. So that's okay with our 70-hour hibernation survivability. And then this is just some example of the kind of filters that our mission operations team are developing on their mapping tools and traverse planning tools. So they're able to apply different filters, such as, for example, they apply a filter where they see only areas where the lander could land. They apply a filter where you see where the Earth is basically not that close to the horizon, right? I think our margin is about 2 degrees. So I think the maximum elevation for Earth is about 10 degrees. So they can apply filters on, okay, where the Earth might be less than 2 degrees, let's not go there. ISRU areas, slope and navigability, so areas that have a lot of slope, let's not go there. So they can apply filters on top of other filters to see what are the options, like where could we go, right, after we apply all these filters. And then finally, okay, this is A51 for me. I can just go probably quickly. I just kind of copy pasted these from a chat that I had the other day with one of the directors. I was just describing what I'm doing. So my, sorry, I missed the R of VIPER. Oh, no, okay, there we go. So yeah, currently I hold the VIPER risk manager position. So my day-to-day duties is basically, you really have to stay in touch with the whole team. And the whole team is big. There's science team, there's the system integration and testing team, there's the rover team, there's a mission operations team. So it's very broad. There's project management as well. So you have to be in close communication all the time, trying to ask, like, are there any concerns? Could there be any risks? So I do risk identification sessions with them. Then there's the whole process of evaluating and scoring how critical your risks are. And we normally do that with assessing how likely the risk is and how severe the consequence of the risk could be. So I do tracking and control of these risks. I also help the teams come up with mitigations and ways to research more of the risks. So that's my day-to-day as a risk manager. Then I'm also in the MSc team, which is the mission systems engineering teams, like high-level systems engineering. So I've done a lot of things within this team. I've helped from data budgets to power budgets to coming up with the sequence detail of operations when we just go do a specific activity. Oh, let's go drill, right? So what is the first thing we do? Okay, we deploy the reel. Is the drill on now? Okay, then let's command to do one bite of 10 centimeters. So, like the specific sequence of things, how they happen. Also, what are the things that could go wrong during each of these steps. And then another type of work that I've been spending a lot of my time lately, probably about 70% of my time, is fault management. So basically, you grab your system, and not just your system, also your processes. So your mission operations, for example, your systems on ground that you use to communicate, and you do an assessment of everything that could fail. And then it's similar to risk management. You try to come up with the things that can fail, and then how likely they are to fail, how severe the effect is to the mission, and then how mitigatable it is. So how much you can do about it to fix it. And then you have to come up with a way to detect this. If it fails, how are you going to detect it? What telemetry are you going to watch? Then how are you going to understand what caused it, which we call isolation. You need to isolate the trigger of the failure, and then your response. What are you going to be able to respond? And so of all these, of course, there's going to be thousands and thousands and thousands of faults. So you have to prioritize what you want to actually work on handling, what you want to maybe have your rover be able to respond to it automatically, which we don't have many things, because our rover is mostly purely commanded. There's very little automation in a rover. One of the reasons is we don't have a lot of budget, we don't have a lot of mass, and then you need to figure out, right, what these faults you want to manage, and have a complete contingency procedure document on ground on, you know, how to quickly go and say, okay, this could be this, you guys figure out how to respond to that or whatever. So it's a really interesting and also really multidisciplinary area, and I actually enjoy it a lot. It's just a lot of work. And then these are other tasks that I think I already mentioned: the data budget, the OpsCon, power budget. This is just one of the, I think actually this is one of the old models of the rover. Not the rover, this is a mobility platform. It's just for testing on the regolith. So they have lunar simulant regolith in the Glenn Research Center in Ohio, and they test the mobility. Hopefully it shows. So it kind of goes very slow though, the video. This is one of the old versions. Now I have new videos, but I don't know if they've been made public though. That's why I didn't use them. And I think that's it. So any questions?
Thank you very much, Mercedes. That was a really interesting presentation. Thank you for bringing us closer to the moon and introducing VIPER to us. It's a very interesting mission. We'll be following the next steps, and we wish you all good luck for the launch in a couple of years. And we'll be looking forward to hear more. Maybe you can give another talk in a couple of years and explain us more in detail how things are going. Mm-hmm. So we have a couple of minutes for questions from the audience. Reminder, please just write the questions on the chat and we'll go through them. But since I have the word already, I'll start asking a question myself directly. So when you were a girl, did you already know what you would like to become?
So I think it was pretty early on that I really liked just space stuff. I think since I was, my dad always tells me this story that when I was a little baby, and he would be, so I was born in 1992 when the Barcelona Olympics took place. And my dad was telling me, yeah, I didn't care about the Olympics. I was with my girl, with the trolley, giving you a walk. And he used to say that I used to see the moon and I was like trying to grab it with my hand. And then when I was a bit more grown up and I could walk, I would get off the trolley and like get on the road trying to like grab the moon. But anyway, probably since I was a kid, I was always very like interested on the space, and I was always asking myself, but what's out there? Like, do you think we're alone? Like, what do you think they are? Like, why are they so bright? the stars. And so I had a lot of curiosity for space, and honestly, a couple movies, that I was really obsessed with, like the movie of Contact. I don't know if you've watched it. It's a great space movie. It's probably one of my favorite movies. and yeah, the whole like astronauts and the Apollo astronauts. And so I knew I wanted to be an engineer fairly early on because I really liked math and nature sciences when I was in primary school, and then with physics and chemistry. So then I was like, yeah, I think I'll try to do aeronautical engineering. And so yeah, it was fairly early on probably.
Okay, so congratulations then from getting to there to where you are now working at NASA. And that links to the next question. How is it like to work at NASA? Would you like to work somewhere else in the future?
So it's probably very stereotypical, but working at NASA is actually great. It's really great. Like probably, and I think most of the people you ask this question will coincide on the answer. That the greatest thing of NASA is the people that work there. Like I remember my first day, I just thought like, why is people so nice? Why are they so like, it's really nice people in general to work with. Really enthusiastic on what they do. Because like you don't do NASA because of the money. You could earn a lot more money in other places. If you are at NASA, probably it's because you really like what you do, because it's also government, so bureaucracy can get in the middle quite a few times, and you might be a bit frustrated. There's a lot of paperwork always for anything you want to do. Even for giving a chat like this, I had to like contact 3 or 4 different people. They had to review my slides, so there's no content that I cannot display, or they also check the general message you want to give. So there's the bad sides of it, but I think the good sides always compensate. And also NASA probably does things that, like, we're not trying to make anyone rich. So yeah, things like spending millions of dollars for trying to understand some science in Jupiter, or how Saturn was formed, like that doesn't make anyone rich. So is the commercial industry going to spend millions on doing that? It's not going to make them like provide any benefit to them economically. So I kind of like that part of it. Like we do our job because of the sake of science and exploration. So yeah, that's another thing that I think is pretty great about it.
Thank you. You mentioned people. Do you think that your career would have been different or even easier if you were a man?
So that's a good question. I think I was pretty lucky to be born in Barcelona. I have to say that, because I didn't really feel, that my professors at the UPC would treat me a bit different. I think they were very well aware that some of the smartest people in the class were actually women. So I didn't have any kind of like, weird feelings. I do have to say that throughout my career, I have encountered a few, and again, that might not be representative, but there are a few individuals that I have encountered where, yeah, well, I would be the one person asking the questions, and they would be replying to like the man next to me. And I was like, no, but I asked the question. Like I would continue to speak, and they were like replying to the man next to me. So I have encountered a few situations in which I needed to prove myself once and twice and 3 times that to prove, hey, I'm here and I'm as good as and valid as everyone else. But I believe, to me, and this is one of the reasons why most of my talks are in schools, actually, it's the general bias in which we grow up in. It's, from cartoons that, they always show that the girl has to be saved by some kind of prince, and it's not the girl fighting or like climbing up the tower to save anyone, or is, from a Taylor Swift video clip, it's like all like the perfect comb hair that probably took an hour to comb that hair with the perfect makeup and perfect dress. Like all these biases is what they start like intoxicating your brain and telling you what you're supposed to be doing, right? I was the type of girl in school that my dad did a pretty good job on that. Like, just like, no, you do what you want, you know. But I used to play football because I really like playing football, and I was not bad at it. And so, but yeah, you know, typical comments like, oh, it's the like boy girl, you know, she's playing football, she's playing with the boys, because you're expected to be like jumping the rope or playing like houses, and you know, someone makes you a gift when you're a kid, and they offer you a doll, or they offer you like a little kitchenette or a makeup set. They don't offer you like a remote control car or something like that, which was my favorite toy when I was a kid, or a Lego, right? So I think it's that bias that, like, as you grow, you absorb, and then it guides you through certain things because you're expected to do certain things. So I think that's, if I could just remove all that or help removing that, that's what I would try the most, for sure.
That's a very nice message. And yeah, we all here on Women in Aerospace are also trying to cope with that. So it's a good message on that. Maybe a couple of more questions on your topic on VIPER. One of the questions is, well, you expect thousands, you mentioned you expect thousands and thousands of failures to happen during the mission that will need to be managed. Why so many? And is there that much uncertainty in the mission?
So it's not that we expect them, it's more that they could happen, right? Anything could fail, from like a snapped harness, from, you know, a soldering that, oh, like, I mean, we do our best with quality control, and we have also an entire department called Safety and Mission Assurance that they check our processes. We have quality assurance. So, you know, in theory, as a harness should not be snapped, or the soldering connection should be good enough, but anything is possible, right? And we have seen this in many missions. Like, failures occur. Like, yeah, you bought a little step motor that is supposed to have a failure rate that is very, very low, but still things happen and it could actually fail, you know. So yeah, and it's not that we expect these failures, is that they could actually occur. And so depending on what the effect is on the mission, if some of these occur, and of course depending on the likelihood, then those are the ones that you want to focus on, the ones that might be more likely, and the ones that might have a higher severity or impact on the mission if they were to occur. Similar with risks, the higher likelihood and the higher consequence, the more efforts you want to put in there.
Thank you. Then we have an engineer in electronics and communications who's planning do a master's in space engineering, since his background is different. Do you have any suggestion if, I'm not sure if it's he or she, sorry, should do a master's in space engineering or aerospace engineering? I'm not sure if you can make there a difference.
So, I mean, what I'm guessing is that space engineering is focused only on space, and aerospace engineering can also include aero stuff, like things that work in the air, like aeronautics part of it. I really don't know what to tell you. I think it's a matter of what you like. I did a master's in aerospace. So, for example, like I took classes like fluid dynamics, computational fluid dynamics, which is, you know, things for fluids. So many applications of computational fluid dynamics are mostly for aeronautics, because you have something that is embedded into a fluid, but in space there's no air, so there's vacuum. So yeah, I think it's a matter of what you like. I think aerospace was interesting to me because it opened my eyes to both aspects of it. And then I was exposed to the space stuff, and then I stayed there. But honestly, I really like the aero part of it as well. So I think it's really interesting. And actually, NASA Ames, they do a lot of the aeronautics. They have some of the biggest wind tunnels in the world as well, which I hear every day in the office. They're very loud.
Thank you. I think that was very good advice. A question looking at the future, the moon and the water on the moon. Do you know if NASA is already planning how to exploit the water if it's found in the south pole of the moon? For example, how would it be transported to a future lunar base?
So I do know there's many efforts already on that, especially probably the Artemis program is exploring and also probably collaborating with commercial industry and private industry on finding ways of how to harvest that water out of the regolith and then how to store it, and in any case, where to store it. Do we want to store it on orbit? So I actually developed a concept for this when it was the Caltech Space Challenge. Caltech is one of the top universities here, and they every 2 years they do a space challenge in which they gather 15 people, I think, around the world, and they put them 1 week together and they give them a problem that they need to solve in 5 days, I think. And so that was one of the concepts, like harvesting the water, then storing the water, and then making basically some kind of refueling station. Like the moon would be some kind of refueling station, because I don't know if you're familiar with how rockets, what they're composed of. So about 90% of rockets are just propellant. And one of the main propellants for rockets is actually hydrogen and oxygen, which is, you put it together, is water. So their products are water vapor. So 90% is fuel, and 90% mostly we use it just to fight the gravity. The gravity is just such a strong pull. And we mostly use everything just to put something on orbit or put it on some kind of trajectory off the Earth. So one of the ideas is, if we could be storing water on the moon, once we have used the 90% weight of a rocket, we could refuel on the moon, and that could enable us going a lot further than we have been able to reach out, because at some point we run out of fuel. So that would be a way to enable a lot further space exploration. So that's one of the reasons why water is so important anywhere else apart from water. Like water in asteroids, another way. So yeah.
Okay, continuing with the water, so the polar characterization and trying to understand where the water and how much is there is the main objective of VIPER. Are there other science questions that maybe VIPER could also answer?
So again, I'm not the science person for the mission, so my answers might not be really accurate. It's mostly understanding as well the form of the water. What is the structural, the structure of this water that we're finding? Is it the same kind of water that we have on Earth? So all these are questions that we will try to provide answers as well for. There's, as I mentioned, there's other science questions that we could try to answer, and it's also understanding how other air planets or like water-bearing planets might be hosting the form of the water. So that might be some, might give us some kind of idea of how other planets might host water.
Then a question, I guess, relating how you test that here on Earth. So for the rover, how are scientists replicating lunar conditions?
Yeah, so this is another good question. It's really, really hard to have what we call an integrated way to test. By integrated, I mean something that can like have all the conditions at the same time. For example, lunar lighting, right? It's very hard to replicate these long casted shadows, very high contrast. So we have what we call the Lunar Lab at NASA Ames, where we can replicate fairly accurately the lighting conditions, but there's only a small box with regolith of like, I think 1.5 by 1.5 meters. So we cannot really move the rover in there. So yeah, we cannot test mobility while being in the lighting conditions, and there is no vacuum in that room, so or thermal environment, right? So it's very hard to do an integrated way to test this. So we have to test the different environments separately. So we have a thermal vacuum chamber, which you can put the rover in a chamber that is pretty small as well. You can barely fit the rover, but you have vacuum and you have the thermal conditions. So we test that on one side. Then we have the slope lab, which is what I showed, is a lab in Glen Research Center where they have simulant of lunar regolith. So the closest they've got to the lunar regolith. And they have a big, it's not huge, but it's a big pool of these regolith, and they can test, they can incline it, they can put rocks and then try to traverse rocks. So we test mobility on that side. But again, there's no lighting conditions, there's no vacuum or the thermal environments. So yeah, it has to be tested on different portions.
Okay, maybe two more questions so it doesn't get too late. How do you value the aerospace sector, both positive and negatively, and its impact in our society? It's quite general.
Yeah, it's pretty general. So positively, I would say one of the cool things about the aerospace sector is that it moves a lot of money and it pushes technology. It really pushes the boundaries of technology a lot. So that technology that is being developed is at some point it reverts into society. Things like from diapers for your babies, the laser for laser eye surgery, laser for your waxing, MRIs, magnetic resonances as well. That came from space industry. So I think that's really cool. And then the other thing is associated to the negative impacts, right? Which you could say like, okay, well, the carbon footprint, right, of some of the things we do, like flying rockets. There are investments into trying to make some propellants more green. There's also propellants that are green because they generate steam, like the hydrogen and oxygen. But I think that's a really, I really don't want to give an answer in there because it's a really tough trade to do. Like we're also putting a lot of Earth satellites on orbit that just like, they help us understand the climate change. They also help us detect fires. They help us help agricultures to harvest better. So it's hard to say, and that has a huge impact, especially the fires and like detection of plastic clouds in the oceans. So yeah, there's some carbon footprint for sure, but there's also a lot of benefit gathered on that other side. So it's hard to assess, like you look at the automotive industry and go assess the carbon footprint of the automotive industry. It's huge. And same with, us just taking a plane overseas, the carbon footprint is huge as well. So it's a tough question, but overall, I think the trend is good. There's more and more investment in trying to stay more like environmental aware of the carbon footprint, and yeah, especially like pushing the technology boundaries. I think it's one of the things that reverse more into society.
Thank you for your vision. So the last question, and it's one I particularly like. We've already asked how things were when you were a girl and you wanted to be where you are now. Let's talk about now when you were a student, already studying aerospace engineering. Did you imagine at that moment that you would be working in a real mission like you are right now? And if you had the opportunity to talk to a young student version of yourself, what would you say to her if you could say something to her in that direction? What would be your message, not just to yourself back then, but also thinking in general about the new generations and the new girls that one day might be in your position?
So yeah, the answer to the first question is no, I did not imagine that I would be working on a mission and working where I'm working right now. Not at all. But I think what I would say to the new generations is anything is possible, like for real, anything is possible. with work and effort and the right attitude. Just keep pushing, keep pushing. If you have a dream, if you have something you like, work on it. Because again, like work is work, right? But work is 8 hours of your day, and then there's another 8 hours that you're sleeping. So you better like what you work on, right? Don't think about the money, or don't think about the prestige or whatever. Think that it has to be something you like, and if you like it, that's what will ensure that you're good at it. Because things that I'm not good at it, I have to say I don't really like them too much. So if you have a passion, work on it. Make up a plan. I usually used to make like plan A, plan B, plan C for something that I would really want to achieve. So make up your plan, lay out your objective, and then try to work on it. Every day you work a little bit on it, at least. That there's not a single day that you don't really work on your objectives.
Thank you. I think that's a great message to conclude today's talk. Congratulations for all you have achieved so far. You have clearly followed your dreams and worked hard to get where you are now. So congratulations for that. And thank you very much for being today here with us, sharing your experience. It's been a pleasure to hear about your project, hearing about the VIPER mission. And as I've said before, we'll be following the next couple of years, and we hope to hear from you then again once you have the first data from your mission. Thank you also everyone for attending today. It's been once again one Woman for Space talk. We're having another one next month. I'm sorry, I don't recall the date. I don't know if one of my colleagues can jump into that and has the information. 10th of June. We'll have the next one, so just follow us on social networks and you'll find out more about our next talk. So with that, I'd like to conclude today's session. Thank you, Mercedes.
Thanks a lot, my pleasure.
And hope to see you all next month for the next talk.
I'll try to connect as well on the June 10th.
Okay, yeah, join us anytime from now. And if anyone is interested in working closely with us, also can contact us. We're happy for any collaboration from anyone interested in space and yeah, bringing this passion all to little girls and women in the sector. Thank you all. Have a nice weekend and see you hopefully then next month.
Thanks a lot. Thank you.